Hey guys, Mr. Martin here, back here with today's video on how to use isosceles and equilateral triangles. Let's get started. Before we go too far, let's remember some key vocabulary. Okay? In the first video of Unit 4, you learned that a triangle is isosceles if it has at least two congruent sides. When an isosceles triangle has exactly two congruent sides, then those sides have some special names, and we're going to talk about those, okay? The two sides that are congruent, when there's only two sides that are congruent, are called the legs. Those legs, of course, come together at a vertex and they form an angle. Okay? That angle that they form is called the vertex angle. Okay? The third side, meaning the last side that's not congruent to the other two sides, okay, is called the base. Normally you'll see the base put on the bottom, but that base can be rotated any which way. It could be on the top and the vertex could be at the bottom. The vertex angle could be at the bottom, okay? And then the two angles that are adjacent to the base, guess what we're going to call those? You know how creative we are with names. We're not trying to be creative, we're trying to be kind of obvious. Those two angles that are adjacent to the base are called base angles. All right? So just some key vocabulary that you need so that when we're talking about isosceles and equilateral triangles, you'll know what we're talking about. Let's get going. Okay, first theorem. This theorem is pretty easy. It says if two sides of a triangle are congruent, then the angles opposite them are congruent. Okay, when we say opposite to them, we say the non-adjacent angles, right? The non-adjacent sides. So if we're talking angle B, then that is side AC. Okay? If we're talking angle C, that is side AB. Okay? So it says, if two sides are congruent, then the angles opposite them are congruent. So we call that the base angle theorem. It simply says if the two sides are congruent, the two base angles are congruent. Kind of makes sense, right? All right. Let's actually apply this and see what we can do. Okay? I told you at the beginning that sometimes they'll rotate it so the base isn't necessarily at the bottom of your triangle. So you want to make sure that you identify the base. It's the non-congruent side, right? So I'm going to mark the base with a blue mark. Okay? So there's our base. So if you need to, you can rotate that until the base is parallel with the bottom of your paper. Okay? If you can do that mentally in your mind, that's fine. If not, you can just rotate that and make that the bottom of the triangle. Okay? And then once you do that, I think you can see that the base angles are the ones that are adjacent to that base. So it's going to be this angle here and this angle here. Okay? So the base angles are angle E and angle F. Not too hard, right? All right. Let's look at the proof of the base angle theorem. This is another example of us using congruent triangles. This one's going to be one of those ones where we have to draw an auxiliary line. Do you remember talking about auxiliary lines? It's a line that was not given in the original diagram that needs to be added in order to prove the theorem we're trying to prove. That line I'm talking about is JM. Okay? M's got a special place though. M is actually the midpoint of that base. Okay? So it is the midpoint, meaning that KM and LM are congruent. I think you can start to see we've got some congruent triangles already forming. Okay? If we could get one more side or one of the angles congruent, then we could have two congruent triangles. Okay? But I think you can already tell that we have a side. That's right. JM on both of those triangles is the same side. So JM is obviously congruent to, you guessed it, JM, thanks to the good old reflexive property. Okay? So our plan is we're going to draw JM so that it bisects that base. Okay? We're going to use side, side, side because we have that third side congruent on both triangles. And we're going to prove that the two triangles are congruent by side, side, side. And then last thing, we're going to use our favorite, or at least my favorite acronym, that CPCTC. Yeah, we're going to use that to prove that those base angles have to be congruent. So here we go. Okay, so the first thing we're going to do, like I said, is we're going to put the midpoint on KL. There is only one midpoint. It's the point that is that bisects that side. Okay. Then through that point, there is only one line through point J as well. Any 2 points determine a line, right? Okay. Now we've got the definition of the midpoint. Since we made M the midpoint, we say that KM or MK is congruent to ML. Okay. If you're kind of keeping track at home, you can see that step 2 knocked off A on our proof, on our plan. Okay? Then we're going to bring in the given information. We hadn't done that yet. You could have done that at the very beginning, but I think you're going to see that they're bringing them in one at a time so we can get a side going. Okay? And then finally, the reflexive property tells us JM is congruent to JM. And so now we've got a side, and a side. Okay? I think that's why they waited to bring in that given information so they could have side right in order. Doesn't have to be in order, but it makes it a lot nicer. So now we knocked off B on our proof, or our plan for the proof. Okay? We've got the two triangles congruent. Now we know that because the triangles are congruent, those corresponding parts are congruent. Remember, the order that we write the letters in matters. Okay? We knew from the vertex that, from the midpoint, that MK was congruent to ML. Okay? So we have to write those two letters together on each triangle. Then we also knew from the reflexive property that JM was congruent to JM. So JM is congruent to JM. So those letters have to be written in that order as well. Okay, so I think you can see the only way I can write JM together and MK together is I have to write JMK. Okay, and the only way I can write JM and ML together is I have to write JML. Okay, so now we can tell the corresponding parts. And K and L are the corresponding parts because those angles are the third angle in each triangle. So we now know that angle K is congruent to angle L, which is exactly what we wanted to prove because those are the base angles. Not too bad, huh? All right, let's keep moving on. Real easy one. It's the converse of the base angle theorem. You guys remember the converse is where we exchange the hypothesis and the conclusion. The base angle theorem says that if the triangle is isosceles, meaning that it has two congruent sides, then it has two congruent angles, right? This converse says if it has two congruent angles, then the sides have to be congruent. It's simply the converse. We have switched the hypothesis and the conclusion. The original theorem had sides right here and angles right here. So all we've done is flip-flop those two things. All right? Not too hard. Okay? Some corollaries. Remember, corollaries are things that kind of fall out of theorems kind of easily or naturally. I think you can see that if we use B and C, okay, being the base angles, because remember, this is if we say this triangle is equilateral, we have all three sides. But let's take those two sides. Then we know that those two angles have to be congruent. Okay? But if we kind of rotate that on our paper and we say that we're going to take this side and this side, okay? Now we've got these two angles being congruent to each other. So I think you can see that we have all three congruent angles congruent to each other. So that makes this triangle equiangular. Okay? So if it's equilateral, then it's equiangular. Okay? Now the converse of that is, if it's equiangular, then it's equilateral. We could do the same thing. If we take these two base angles being congruent, it proves that these two sides are congruent. Rotate it on your paper, and now we've got these two being congruent, and it proves that these two are congruent to each other. Okay? So now we've got all three sides being congruent to each other. So this is now an equilateral triangle. So the corollary to the base angle theorem says that if it's equilateral, then it's equiangular. Okay? And then the corollary to the converse says if it's equiangular, then it's equilateral. I think those are things that we've all taken for granted. Now we're just, again, giving them a fancy name. All right. Last thing I want to do is I want to look at the angles of an equilateral triangle, and I want to prove that those are actually 60 degrees. Right? So we know that if it is equilateral, right, then it is also equiangular. We just got through talking about that. Right? So we know that in triangle PQR, angle P is congruent to angle Q, which is congruent to angle R. Or another way to say that is the measure of angle P equals the measure of angle Q, which equals the measure of angle R. We're turning those into the measures so that we can actually do some math on it. Right? So if all three of those are equal, we really have three measures of angle P. Because we're just going to take out Q and put in P. We're going to take out R and put in P. You remember from the triangle sum theorem, it says that the measure of angle P plus the measure of angle Q plus the measure of angle R equals 180 degrees. Remember that? So we're just going to take out P and we're going to put it in take out Q and put in P. And then we're going to take out R and we're going to put in P. And now we've got three measures of angle P. Divide both sides by 3 and you can see that the measure of angle P is equal to 60. Well, but that's also Q and that's also R. So you can say the measures of the angles of a equilateral triangle have to be 60. Okay? I don't think this is really hard information. I think it's, again, information that we may have known, but we're given, the proof to it, and we're showing why this stuff is true. Not just understanding that it is true, but we're explaining why it's true. I think it's so much easier to remember stuff if we understand why it's true. It's easier to remember that it's true. Okay? If you remember the isosceles triangles having a base, it's pretty obvious that those base angles have to be congruent to each other. Likewise, if you remember a triangle is equilateral, you can remember that it's also equiangular. Okay? There you go, guys. So take good notes on this video. I hope that you're going back and pausing and rewinding. If you have any questions, write those down and let's talk about those in class. We'll see you in class.